Right now, while you're watching this video, a spacecraft built by a tiny startup with fewer than 50 employees is hurtling through the void, on its way to an asteroid worth more than the entire global economy. This isn't a movie, this isn't a concept, this is happening in 2026, and the companies behind it are about to change civilization. Welcome back. If you've been following the space industry, you know we're living through a moment that historians are going to compare to the invention of the printing press or the discovery of oil in Pennsylvania. Because somewhere out there, drifting silently between Earth and Mars, are asteroids packed with rare earth minerals: neodymium, cobalt, platinum, iridium. The exact materials powering your phone, your EV, your solar panels, and every piece of modern technology you depend on. The problem? We're running out of them on Earth. Mining them here is destructive, expensive, and increasingly political. But in space, they're just floating there, unclaimed, untouched, waiting. So today, we're going deep on the actual companies, the actual technology, and the actual mission timelines that are making 2026 the year asteroid mining stopped being science fiction. To understand why 2026 is the inflection point, you need to understand what changed. For decades, asteroid mining was trapped in a fantasy loop. Brilliant idea, impossible economics. Getting a kilogram to orbit cost tens of thousands of dollars. A full mining operation? You're talking about investments in the tens of billions with a payback horizon of decades. Nobody would fund that. But three things just broke that deadlock simultaneously. First, launch costs collapsed. SpaceX's reusable rockets have cut the cost of getting to orbit by more than 90% over the past decade. That changes the math on everything. Second, autonomous robotics matured. The machine learning revolution didn't just give us chatbots, it gave us robotic systems that can make real-time decisions millions of miles from the nearest human operator. No comms lag workaround needed, the robot figures it out. Third, demand exploded. The green energy transition isn't just a policy preference, it's a physical requirement. A single offshore wind turbine requires around 600 pounds of rare earth elements. Electric vehicles use neodymium magnets, advanced batteries need cobalt. Global demand for these materials is projected to increase 400 to 600% by 2040, and terrestrial supplies simply cannot keep up. That gap is where asteroid mining becomes not just viable, but necessary. So who's actually doing this in 2026? Let's talk about the real players. Astroforge is arguably the most watched company in the sector right now. Based in California, they've already launched their first demonstration mission, a small spacecraft called Brocker 1, which tested metal processing technology in orbit. But 2026 is where things get serious. Their next mission, Brocker 2, is targeting an actual near-Earth asteroid for close-up reconnaissance. The plan is to fly alongside it, scan it using onboard spectrometers, and prove that a commercial spacecraft can identify and confirm the mineral composition of a real space rock. They're not mining yet, but this is the prospecting phase, and it's real. TransAstra Corporation is taking a wildly different approach, and honestly, it might be the most elegant engineering solution in the whole industry. Their concept, called the optical mining system, uses concentrated sunlight, essentially giant solar concentrators, to superheat sections of an asteroid. That vaporizes volatile materials like water and carbon compounds directly from the surface. No drills, no mechanical excavation, just focused light. In 2026, they're progressing towards demonstrating this in low Earth orbit with a scaled test system. The applications are enormous because if you can extract water from an asteroid, you can split it into hydrogen and oxygen, and suddenly you have rocket fuel manufactured in space. That's the cosmic gas station concept, and it makes the entire solar system accessible. Karman and several other well-funded stealth players are focusing on the infrastructure layer, the orbital processing depots, the robotic transfer systems, the communications architecture. Because here's something most people miss. Asteroid mining isn't just about getting the minerals. It's about building an entirely new supply chain from scratch, in space. Let's walk through what an actual 2026 era mission looks like, step by step, because the logistics are genuinely mind-bending. Step 1 is target selection. Near-Earth asteroids, the ones whose orbits bring them relatively close to our planet, are the primary focus. Not because they're the richest, but because the delta V, the velocity change required to reach them, is manageable with current propulsion technology. Some of these asteroids are actually easier to reach than the Moon. Missions use ground-based and space-based telescope surveys to catalog candidates, then classify them. C-type asteroids are rich in water and carbon. S-types carry stony silicate materials with nickel and iron. M-types are the jackpot. metallic asteroids potentially loaded with platinum group metals. A single M-type asteroid just 500 meters in diameter could contain more platinum than has ever been mined in all of human history. Read that sentence again. Step 2 is Scout Probe. You don't send your billion-dollar mining hardware to an asteroid you've only seen through a telescope. You send a small, fast, inexpensive reconnaissance spacecraft first. This probe enters orbit around the asteroid and performs a full survey, radar mapping, spectroscopic analysis, gravitational field measurement. It's building a three-dimensional model of the rock, identifying where the valuable deposits are concentrated, and flagging hazards like loose regolith or unstable terrain. This is your treasure map. You don't dig without it. Step 3 is extraction, and this is where the engineering gets exotic. Forget human miners in spacesuits. Every piece of this is autonomous robotics. For surface mining, robotic vehicles anchor themselves to the asteroid using harpoons or electrostatic grippers because gravity on a 500-meter rock is almost non-existent. They use drills or laser cutting systems to break material loose and feed it into collection chambers. For interior deposits, shaft boring robots drill central access tunnels and use magnetic separation to pull metallic fragments toward collection points. Some proposals use directed energy, lasers, to thermally fracture and soften sections of solid metallic asteroids before mechanical arms harvest the material. Each method has trade-offs, and the right approach depends entirely on what the asteroid is made of and how it's structured. This is exactly why the prospecting phase matters so much. Step 4 is on-site processing. This is the real game changer, and it's the part that makes the economics work. You cannot afford to ship raw asteroid rock back to Earth. The mass is too high, the value per kilogram is too low. So the refinery goes to the asteroid. Mobile processing units on-site use magnetic separation to isolate iron and nickel, electrolysis to break down more complex compounds, and thermal processing to concentrate precious metals into dense, pure ingots. Water extracted from C-type asteroids gets split via electrolysis into hydrogen and oxygen, breathable air for future crewed operations, and more importantly, high-performance rocket propellant. This is the foundation of the in-space economy. Process it there. Ship only the dense, refined, ultra-high-value payload home. Step 5 is the return. Finished product, platinum bars, refined rare earth element concentrates, gets loaded into specialized cargo pods. These pods use low-thrust, high-efficiency ion propulsion for the long transit back. As they approach Earth, they don't land conventionally. They enter high orbit, get retrieved by a space tug, and are either brought to an orbital processing station or transferred to a re-entry vehicle for ground delivery. The entire chain, from asteroid to Earth, forms a supply network spanning hundreds of millions of miles. Here's what this means for the world. The rare earth minerals in near-Earth asteroids could end the geopolitical stranglehold that a handful of countries currently hold over the materials that power our entire civilization. They could make green energy technology genuinely abundant and affordable. And the water and propellant extracted in space, that builds the infrastructure for permanent human presence throughout the solar system, space stations, lunar bases, Mars missions, without needing to haul every kilogram of fuel out of Earth's gravity well. The legal framework is still catching up. The 1967 Outer Space Treaty is being actively reinterpreted. Nations including the United States, Luxembourg, and the UAE have already passed domestic legislation affirming that private companies can own resources they extract in space, even if no one can claim sovereignty over the asteroid itself. The rules are being written right now, in real time, by lobbyists and lawyers and international negotiators. The challenges are enormous: the investment requirements, the technological risk, the regulatory complexity, but the direction is irreversible. 2026 is the year the proof of concept missions launch, the year the data comes back, the year we find out whether the math actually works. And if it does, the first company to close the full loop from asteroid surface to Earth delivery won't just build a business. They'll build an industry that defines the next century of human civilization. The treasure is out there, and humanity is going to get it. If you found this genuinely mind-expanding, subscribe. We cover the frontier of science and technology every week. Drop a comment below. Which company do you think closes the loop first? See you next time.